Once we've seen all of the chain rule compilations, along with what we've seen earlier, such as the product rule, the quotient rule, how to take derivatives of polynomials, how to take derivatives of e to the x, how to take derivatives of natural log, and so on and so forth. Now what we can do in these last few slides is we can combine all of our rules and deal with very complex functions. So we can find the derivative of very complex functions by combining lots and lots of our rules. Let's take a look at example 6. So example 6 is r of x equals 6x to the third times cosine of 8x squared. So we have a lot going on there. We have a polynomial times cosine, and in the argument of the cosine is another polynomial. Well, we can use the chain rule and the product rule at the same time to find the derivative of r of x. Here is r of x. So we have to view this thing as, first off, a product rule, where 6x to the third is our first function, and cosine of 8x squared is our second function. Now, we should know that the product rule, if we write this as f times g, the product rule says to take the derivative of f times normal g plus normal f times a derivative of g. In our case, we can do that. So derivative of f, let's call the 6x to the third the f function. So we take the derivative of that, that is 18x squared, multiplied times normal second function. The normal second function is cosine of 8x squared plus normal f, so normal 6x to the third, times the derivative of g. Now, derivative of cosine, we know is negative sine, but we have an argument on the inside. So in order to take the derivative of g, we need to apply a chain rule. So it's negative sine of 8x squared multiplied times the derivative of the inside function, which is 16x. So the derivative of r of x is equal to 18x squared cosine 8x squared plus 6x to the third times negative sine 8x squared times 16x. I am going to clean this up just a little bit. I'm going to rewrite that so it looks a little bit nicer. I'm going to throw off the parentheses of 18x squared. So just take 18x squared times cosine of 8x squared plus, so we have a negative sign, a 6, and a 16. If you take 6 times 16, you get 96. So we get negative 96x to the fourth multiplied times sine of 8x squared. Again, the 6 times 16 gave me 96. I had a negative with the sign. And then the x to the third times the x gave me an x to the fourth. So my derivative is 18x squared cosine 8x squared minus 96x to the fourth times sine of 8x squared. And once again, that required us to do a product rule, but inside of the product rule, to find this g prime, I had to utilize a chain rule in order to find it. So we could take a chain rule and combine it with a product rule and figure out derivatives. Let's take another example. Let's take q of x is equal to e to the 5x divided by natural log 6x squared plus 2. And let's use the chain rule along with the quotient rule in order to find the derivative of q of x. All right, so I have my q of x. And I'm thinking of this q of x in terms of a chain rule and a quotient rule combined. That means I want to think of the numerator as f, the denominator as g. Think about what's going to happen with the quotient rule. Well, when I take a derivative, what happens is I get a fraction, which is f prime times normal g, minus f times g prime divided by g squared. Every time I take a derivative of f or g, I'm going to have to utilize the chain rule. So let's take a look, see if we can do this. Q prime of x is equal to derivative of my numerator is going to be 5 e to the 5x. Normal denominator is going to be natural log of 6x squared plus 2 minus normal numerator is e to the 5x. And then the derivative of the denominator. Derivative of the denominator is 1 over 6x squared plus 2 multiplied times the derivative of that function, which is 12x. So it's 12x over 6x squared plus 2. And that all is going to have to be divided by the natural log of 6x squared plus 2, the entire thing quantity squared. Now, obviously, this looks like a big, ugly mess. And it is in some ways. Obviously, this is a really complicated derivative function. The point of this is to see that it can be done. You can start with really complicated and nasty looking functions, and you can combine your rules in order to find derivatives, even though that sometimes these derivatives are pretty ugly looking. So what I'd like you all to do is find the derivative of L of x. Using the chain rule with the product rule, with our basic derivative rules, find the derivative of L of x here.